So our first topic of this year is limits. We really have three topics for the year. First topic is limits. Second topic is derivatives. And the last topic of the year is integrals or antiderivatives, so we call them. So we're going to spend about a week and a half probably on limits and then move into derivatives for most of the rest of this quarter. So when we talk about limits, what we are looking for is a value, a y value of our function that we get very, very close to as x approaches some number. So I've got this lovely little picture here of some function y equals f of x. And I am having my x values, whether they're less than a or greater than a, I'm having them approach some constant, some number a. And we would say that the limit, that's an LIM, the limit as x approaches a, that's how this is read, the limit as x approaches a of f of x, so the limit as x approaches a of our function is equal to whatever this height of our function is there, whatever L is, and L is just a number. This is the notation that we're going to be using for the next couple of weeks here as we talk about limits. This is a limit notation. The limit as x approaches a of f of x is equal to L. So what that means is that as my x values get very, very close to a, my y values get very, very close to L. That's all that means. Okay? That's literally all that it means. As x gets close to a, f of x gets close to L. So if I had some function, like let's say the function y equals x. Everybody's familiar with the function y equals x, I hope? Yeah? No?
Yes.
Yeah, see, that was good. Somebody, I don't know who that was. They unmuted themselves and said, yes. Nice work, somebody. All right. I can't see who's talking. I can't see your face. It doesn't show me who it is. So, oh well. Let's say we were interested in the value at 2. We could say, what is the limit as x approaches 2 of this function x? Well, what is the y value get very, very close to as the x value gets very, very close to 2? As the x values get close to 2 here, coming from either side, what is my y value getting close to?
2.
Getting close to 2. We would say the limit as x approaches 2 of x, that's my f of x, right, is 2. If I said, what's the limit as x approaches 3 of x, what would the answer be?
3.
3. That's great. If I said, what is the limit as x approaches negative 1,000 of x, what would our answer be?
Negative 1,000.
Wow, that's spectacular. You guys are on top of this already. That's great. That's the basic, simple idea behind a limit. What does a function get close to as the x values get close to some number? Now, there's a little bit more to it than that. There's a little bit of like formal defining of what a limit is. And so that's what's on this first page here.
So we define L, correct?
Say that again?
We define L.
What do you mean you define L? I mean, I'm gonna say what's the limit as x approaches some number, and you will tell me what L is.
Okay. So yeah, okay.
Yeah, does that answer your question or no?
For now.
Okay, yeah. We're gonna, it'll all, it probably seems a little convoluted or confusing at the moment, but it'll make more sense in a bit, I think, once we start really doing it with other functions. When we start looking for limits, because limits are the whole basis of calculus. You can't do derivatives and you can't do integrals and antiderivatives without limits. Once we start looking for a limit, we kind of have to ask ourselves 2 questions, and that's what we've got here. There's 2 questions that we want to ask ourselves. As x gets very, very close to a, so as we get very close to whatever x value we're interested in, does our function get very close to some real number L, right? So an example of why it might not, well, maybe as x approaches 0, right? Maybe my function is going towards an asymptote, right? Maybe I have a vertical asymptote here, and I'm not approaching some real number L. Okay? So if I'm not approaching a real number, then we're not going to have a limit at that value. Okay? But if I just have some function that's doing this as x approaches 0, well, yeah, I'm approaching some real number L, right? And the second part of it is, can I get as close to that number L as I want to by choosing numbers very, very close to x equals a? And that part we'll worry about in just a second. That's the second question we ask ourselves. And if we can answer yes to both those questions, then we say that this is true, that the limit exists, and the limit is whatever that L value that we're getting very close to is. Okay? So the most important part of all of this, we'll say the most important part. The most important part of all of this is that the function does not have to exist at x equals a. The function does not have to exist at x equals a. Okay? It just has to, as we get very, very close to a, get very, very close to some number. And we're going to look at what that means in a second. But if you look at my picture, did my function exist at x equals a?
No.
No, it didn't, right? I had an open circle there, and that's okay. So long as I am getting close to some number L. I don't have to get to that number L. I just want to be getting close to some number. It's all about what happens on the very, very, very tiny intervals surrounding A. It's not about what happens at A. Limits have nothing to do with what happens at A, only what happens as you get very close to A. Everybody good with that? It's a little bit weird, maybe, because all the way up until this point in your entire life doing math, you're concerned about what happens at this point, what happens at that point on a function, right? How can I find the x-intercept, some point on the function? Well, now we're not interested in the point, we're interested in what happens as you get close to that value. It's kind of a shift in how we need to look at math in general. Everybody good with that or no?
Yes.
All right, spectacular. Let's move forward then. If you have a continuous function, a function that is continuous at the value x equals a, then it's very, very, very easy to find a limit. The value of the limit as x approaches a of a function is just f of a if the function is continuous. So you think about some nice, simple, easy function like 2x minus 3. Is 2x minus 3 a function that is continuous for all real numbers?
Yes.
Yes.
Yeah, this is just linear. This is continuous. Sorry about my handwriting. It's always bad, but it's even worse on the laptop screen. So this is continuous for all real numbers, which means that the limit as x approaches 4 just ought to equal the function evaluated at x equals 4. And this is how I'm going to notate this. I may put brackets around things, or I may put parentheses around them, or I may just put like this for this one. I may just put a vertical bar at the end of the equation and write x equals 4. That means this function or this expression evaluated at this number. So what does that become? That becomes 2 times 4 minus 3, or there we go. Just making sure you all are in the right class and know how to do arithmetic. Okay. Everybody good with that? We wanted the limit as x approached 4 of 2x minus 3. All we had to do was plug in the 4 because we knew this function was continuous. Now, real quickly, and I'm going to do this often enough, I'm going to pop open Desmos. You're all familiar with the Desmos on the internet and the interwebs, that thing with all the websites, right? Right, Desmos. So if you're not familiar with Desmos, you should get familiar with Desmos. It's desmos.com, I think /calculator or something like that. Can you all see the blank Desmos there?
Yes, we can.
Yes.
Spectacular. Okay. They also have an app for your phone, and much to my wife's dismay, the first thing I downloaded when I first got a smartphone, whenever that was years ago now, I downloaded Desmos on it. That was the first thing, because very important. So here's my function 2x minus 3. And what were we looking at? We were looking at the limit as x approached 4, and we'll note, I can't click on 4 exactly. There we go. There's the 0.45. 5 was what we got as the limit. It's just the y value of our function there because our function is continuous. Right? Everybody good with that?
Yeah.
All right. Now I want to think about this in terms of the definition. We said there's some number 5 that we're getting very close to as x gets close to 4. Can we get as close to 5 as we want to get by picking numbers very, very close to 4? So if I pick, so suppose I wanted to get to like 4.99999 for my y value. Could I get to 4.99999 for my y value by picking a number of x very close to 4?
Yeah.
Yeah, all we'd have to do is just say, okay, y equals 4.99999 and solve for x, and then we'd have that x value, right? What if I wanted to get to 4.9999999999999? Could I get that close?
Yes.
Yeah, I would just have to figure out an x value that makes that work. I can get as close to 5 as I want on either side. I could pick 5.0000000000000000000000000000001, and I could get that close to 5 by picking a number that was just a tiny bit more than 4. Okay, everybody good there? That's good for everybody. Everybody's all right.
Yes.
Spectacular. Okay, cool. Well, then let's think about this next one. We've got the limit as x approaches -3 of x squared plus 1. What do you know about the function x squared plus 1?
It's quadratic.
It's quadratic, right? It's a polynomial function. It's a parabola, or it's a parabolic function. What do you know about all polynomial functions?
I guess it has coefficients and it can start with different degrees.
Okay, so we got different degrees on them, right? They got, we probably learned about the end behavior of them, that kind of stuff, right? Probably a number of things you know about polynomial functions. The most important thing that you want to know about polynomial functions for this class, for right now, is that all polynomial functions are continuous for all real numbers. That's the biggest thing you want to know when we're talking about limits, is that all polynomials are continuous for all real numbers. There is not a single number that I cannot plug into x squared plus 1, right? I can take any number, positive, negative, or 0, square it, and add 1 to it, and I will always get out a y value. There's never any discontinuities, right? There's never asymptotes on polynomial functions. There's never there's never a break in the function, right? Unless we define it for only a certain domain, which we're not doing here. This polynomial function is continuous for all real numbers, which means its limit, and the limit as x approaches 3 of it, should just equal the value of the function at 3. And what's -3 squared plus 1? It ought to be
10.
10. Excellent. Everybody good with that?
Yes.
Cool. What about this radical function? The limit as x approaches 7 of root x plus 2. Is that function continuous for all real numbers?
No.
No, it's not. What is the domain of that function? How can you find
-2. Oh wait. Yeah.
the domain of this ought to be -2 to infinity, right? And
Yeah.
can we include -2 in that? -2 with a bracket.
Yep.
Right, to infinity with a parenthesis. That's the domain of that function. And are radical functions continuous on their entire domain, or are there discontinuities within them?
It's continuous otherwise.
Yes, on its domain, it is continuous. So we'll say that this function is continuous on -2 to infinity. Is 7 included on -2 to infinity?
Yes.
Yep. And so all we have to do is plug in our value of 7, get the square root of 7 plus 2, which is
3.
3. Good. And I want to make a point about this, that when we talk about the square root of 7 plus 2, or the square root of 9, it's 3. It's not -3. If I was looking for the negative square root of it, I would put a negative sign out in front of it. I am not looking for the negative square root. If we are solving an equation, if I said x squared equals 9, then you better tell me x is plus or minus 3. But if I just have a square root, don't tell me that this is 3 or -3. Tell me that's 3. Right? It's the principal square root. It's the positive square root. Everybody good with that?
Yeah.
Perfect. All right. Okay, now we're going to do some really, really difficult work here. We're going to take a look at this very difficult function, 2x plus 1, and just make sure we've all got this solidly. What's the limit as x approaches 3 of f of x? I didn't hear what that was. I didn't hear what you said. Sorry.
7.
That's right. It's just 2 times 3 plus 1. This is a continuous function. We plug in the 3. Easy. What about -3? Still continuous function. Plug in the -3. What do we get?
-5.
-5. Still a continuous function. Plug in the 0. What do you get?
Positive 1.
1. Easy. And we'll note that those are the values, right? At x equals 3, it's 7. At x equals -3, it's -5. At x equals 0, it's 1. They're all just points that are on this linear function. Good?
Yes.
Cool. All right. We're going to start to make this slightly more difficult. You don't need to graph all these right now because I'm just going to do it for you. In fact, I've already done it. This one is easy. The function is f of x equals x plus 2. What's the limit as x approaches 1?
3.
3. I hope you all are getting that. The limit is 3. All right, we can get as close to 3 as we want by picking numbers closer and closer to 1. Now, we're going to take a look at this next function, which is x squared plus x minus 2 over x minus 1. And if we were to try to graph that, first thing that we would always do is factor the numerator. What is the numerator factor to?
X plus 2 times x minus 1.
Perfect. And what does that allow us to do?
There's a hole.
Right, it lets us cancel out those x minus 1s and tells us that this function just looks like the function x plus 2, the whole at x equals 1. And so that's what I've drawn here. It's just the function x plus 2. It's the same linear function we had previously, but with a whole at x equals 1. So what's the limit as x approaches 1 of g of x of this function?
3.
3? Everybody agree with 3, or anybody have a different opinion? Should I just put a 3 here and call it good?
Agreed.
Agreed. Okay, so it's okay, like we mentioned before, that there's a hole there, because we can still meet the two criteria. Right? The first criteria was, is there some number that we're getting closer to? Well, yeah, as x gets closer and closer to 1 and gets very, very close to 1, I'm getting very, very close to 3, aren't I? And the y value is still getting close to 3. Does it ever get to 3?
No.
No, and that's okay. A limit doesn't have to get to that value. Like the function doesn't have to get to the limit. You just have to get very, very close to it. And can I get as close to 3 as I want? Could I get 2.999999999 if I wanted to.
Yeah.
Yeah, I just have to say 2.9999999 equals this and solve for x, right? That's all I have to do, and I would get the value. Could I get to 3.00000000000000001 if I wanted to?
Yes.
Yeah, right? I just have to pick something very, very close to 1, just to the right of 1. Right? So it doesn't matter that the point doesn't exist there on the graph. Everybody good with that?
Yeah.
Wonderful. Just for everybody's reference here, if you need to like step away from your computer, laptop, iPad, phone, whatever you're taking class on, you're just welcome to do so. Just if you need to step away to do something for a second, feel free to do that and come back. You don't need to ask, just so you're all aware. Everybody good? Yeah. Okay. All right. Let's take a look at this one. So this is now a piecewise defined function. We've got x squared plus x minus 2 over x minus 1 if x is not 1, which is the function we just had on the previous page, right? X plus 2 with a hole at 1. But now I've filled in that gap. I've said that h of x equals 2 if x equals 1. So what we've got is a linear function except with a hole in the middle of it. And then we have some random point plotted there at the point 1, 2. Everybody good with that being the graph of x squared plus x minus 2 over x minus 1 if x isn't 1 and 2 if x equals 1?
Yeah.
Perfect. Okay. So what's the limit as x approaches 1 of h of x?
Would it still be 3? Because you can get as close as you want to 3.
That is exactly right. It is still 3. I can get as close to 3 as I want. I can still get to 2.999999999 if I want by picking something very, very close to 1. I can still get to that 3.0000, et cetera, 1, right? By picking something just a little bit more than 1. It doesn't matter that when x finally hits 1, the value of the function is actually 2. That does not matter in the least. Right? What matters is what's happening as we get very, very close to x equals 1. That's the whole point of these limits. Is it's not about what happens at the point. It's about what happens as we get very, very close to the point on a very, very tiny interval surrounding that point. Everybody good so far with that? Everybody okay with that being 3 and not being 2? Or not being a does not exist limit, because there will be plenty of limits where the answer is it doesn't exist.
Yeah.
This one is still just 3. Okay, so we'll want to note that in the previous 3 problems, right, the first one, f of 1, the limit was 3 and the function's value was 3. And in the second one, g of 1 didn't exist, but the limit was still 3. And in the last one, h of 1 was 2, but the limit was still 3. Right? So the limit can match up and have the same value as the function. The limit might exist even though the function doesn't exist, or the limit might be some number and the function might be some other number. Right? All of those are okay. The limit can be the value of the function. The limit can exist and the function cannot exist there, or the limit and the value of the function might be different numbers, and that's okay. All good? Everybody okay with that?
Yes.
All right, no questions, no issues, no problems. Everybody's feeling good, off to a good start. Feel like you're not gonna fail? At least not yet. All right. Here we've got f of x equals sine x over x. And this is a function that we're going to come back to multiple times as we talk about limits. You may not be familiar with this function, but there is what it looks like, at least from around -6 to 6. It sort of looks like a sine curve, right? Except that it's going up to 1 here at x equals 0 and then dropping down to far less than, far not less than, but something between 0 and -1. It doesn't actually drop all the way down to -1. If I asked you what's the limit as x approaches 0 of this function, what would you tell me it is?
1.
Okay, 1. Anybody agree or disagree with that?
Agree.
Agree?
Agree.
Is there a value of my function at x equals 0? What happens if I plug in x equals 0? I get the sine of 0 divided by 0, don't I?
Invalid.
Which is what's the sine of 0? The sine of 0 is 0, and 0 is just 0. So we've ended up with this thing that is 0 divided by 0, which is an exceptionally important thing in calculus. This is called indeterminate. Okay? This is called indeterminate. Anytime you end up with 0 over 0, we say that the limit is indeterminate. And there are other forms of being indeterminate, but the most important one that we're going to deal with the most is 0 over 0. Whenever you try to plug in a value into your function to find a limit and you get 0 over 0, you get indeterminate, you have to do more work. You have to do something to simplify that function, something to get around that 0 over 0 to prove that limit. Now, for this particular one, that process is a little bit complicated until we've learned some other tricks. So the best option we have right at this moment is to take a look at the graph, and I'm going to put it up on Desmos. So here's the graph, and the best thing we can do is sort of zoom in around the point at x equals 0 and see if it looks like something weird is happening. Does it look like something weird is happening there? I mean, I know that there's a hole there. Desmos doesn't show the hole, but I know there's a hole there.
But we're not looking at Desmos.
Oh, you're not looking at Desmos. Sorry. I forget to do that all the time. Just ask last quarter. Now you're looking at Desmos, right?
Yep.
Yeah.
Or looking at Des.
You're not?
We are.
Oh, good. Oh, good. Phew. All right. Does it look like at x equals 0 something weird is happening to this function other than the hole that Desmos doesn't show?
Sure.
It does. It looks like something weird. It doesn't look like anything weird is happening to me. I don't know. It looks pretty normal. It looks like just it hits like a little maximum there and then goes back down, right? I mean, we could zoom in and see. And the more we zoom in, the better idea we'd have of what's happening there. If something weird might be happening, like it might shoot up really, really fast, really high, or shoot down really quickly.
It looks normal.
It looks normal. Yeah, it does. It looks normal. Now, and looking at the graph and zooming in on the graph is a good way to have a general idea of what's going on and to make a good guess at what that limit is. And oftentimes you might need to do that if you're having a difficult time proving the limit. And we could be pretty certain that nothing weird is happening. And I've zoomed in pretty far on this already, and it doesn't look like anything weird is happening. We could be pretty certain that that limit is 1. And I will tell you that that limit is 1, right? This limit is 1. But we're going to come back to that once we've got some more tricks, and we're going to learn how to deal with this indeterminate form. Now, there are other indeterminate functions that we can already deal with pretty easily. So we're going to take a look at something like, and you don't need to graph this on your graphing calculator. Normally I'd make people do this, but we're just going to take a look at it together. We're going to look at the function x cubed minus 2x squared over 3x minus 6. So it looks like a parabola, and it's got a hole in it at x equals 2. And you could probably tell that if you factored it out, and you'd see that both the numerator and the denominator have an x minus 2 in them, and those would cancel and give you the hole at 2. So anybody have a good guess on what that limit is at x equals 2?
Limit is just 2.
As x approaches 2, it looks like 2. I think it's between 1 and 2, isn't it? I mean, there's 1. And there's 2.
Wait, Nick, you're talking about wall.
Yeah, we're always going to talk about the y value. Like, what is the y value of function? So what does it look like? What do you guys, anybody got a guess?
1.3-ish.
1.3-ish. I like that. 1.3-ish. We'll write that down. Anybody have a different guess?
4/3.
4/3, not 4/3-ish, just 4/3. Anybody else? No?
5/4.
Yeah.
5/4? We got lots of good guesses. Now we could probably go in here, and I'm going to graph this now into Desmos. What did we have? We had x cubed minus 2x squared. Is that right?
We're not looking at Desmos.
All right. Yeah, good. That's what you should yell at me every time. What was the denominator of it? 3x minus 6? Is that right?
Yes.
X cubed minus 2x squared over 3x minus 6. And you'll see I'll be lazy and just like type x cubed out as xxx. And 2x squared is 2xx, just because it's easier than trying to do an exponent. If I zoom in around 2, and we know that nothing weird's happening there other than there being a hole, right? But as we zoom in around x equals 2, sorry, x equals 2, we could probably get a pretty decent idea. It looks like it's between 1.2 and 1.4. In fact, here's 1.3. It's between 1.3 and 1.4. And Desmos is so cool that I can just like look at a value really close. Just below it, it says 1.332. And just above it, it says 1.3347. So what does it look like it's coming out to be?
4/3.
Yeah, it looks like it's about 1.3 repeating or 4/3, right? And generally I'll use the improper fraction normally. So it looks like that's what it should be. Can we prove that that is what it actually is? Any ideas on how we'll do that?
You plug in 4/3 for x.
No, if we plug in 4/3 for x, that's just going to tell us about what's happening at x equals 4/3, which is somewhere over here.
Basically, you have to factor both of them. So the numerator would be x squared times x minus 2, and then the denominator would be 3 times x minus 2, and then x minus 2 can be in the numerator and denominator can be divided, and then it just ends up with x squared over 3.
Exactly. So we factor out the x squared from the numerator, factor out the 3 from the denominator. We have x minus 2's in them. Now, why is it okay for me to cancel out these x minus 2's? I know that they're the same things in here, but I can cancel them out because one of them divided by the other one is always equal to what? Since they're the same, it's always equal to 1. Well, almost always. When is x minus 2 over x minus 2 not equal to 1?
When x
equals 2.
Right. Equals 1 if x does not equal 2. Well, we're doing a limit as x approaches 2. So what is that telling us? That's telling us that x is getting very, very close to 2, but x is never actually equal to 2, and we don't care what happens at x equals 2. We only care what happens as we get very close to 2. And as we get very close to 2, this division is definitely equal to 1. So we can cancel those out. Everybody good with that?
Yeah.
Okay. So we can say that this limit is equal to the limit as x approaches 2 of x squared over 3, which now reverts back to just a simple polynomial, right? 1/3 x squared. And just plug in our 2 into, which gives us 2 squared over 3 or 4/3. Everybody good or no? Any questions, issues, problems, complaints? Anybody feeling really sad and upset about that? No? Cool. All right, let's do another one. And then I think we'll stop right after this one because I think we're gonna pretty much be out of time. So let's find the limit as x approaches 2 of f of x. And so I'm going to give you a quick rule here. The first thing that you should always do every time, no matter what, when you are trying to find the limit is just plug in the number. Just plug in the number to your function. If it comes out to be 0 or 7 or -3 or 58.1, you're done. If you get a number, you're done. That's it. You just plug in your a value, and if you get a number, you quit. You say that's your answer, you're done. 100% of the time. But if you get something that is indeterminate, then you're going to have to do more work. So let's first plug in 2 to this function. And what do we get if we plug in 2? We get 8 minus 10 plus 2 divided by, what is that? 20 minus 14 minus 6. And what does that come out to be?
Zero over 0.
Oh, right. Darn, that's a bummer. So we didn't just get a number. Right? We got something that's indeterminate, which means we've got to do some more work. It means that this function has a hole at x equals 2. And so that means we can factor the numerator and factor the denominator. And we'll do that. And we should end up with a couple of terms that cancel out. And we should be clued into what one of the factors of the numerator and this same factor should be in the denominator. What factor should that be?
X minus 2.
Yeah, they should both have an x minus 2 in them, since we know that plugging in 2 turns this into 0. So if I have an x minus 2 in the numerator, I'm going to have a 2x, right, to get the 2x squared. I'm going to have a 5x to get a 5x squared in the denominator. And to get a positive 2, I'm going to need to have a minus 1 there. And to get a minus 6, I'm going to have a plus 3 there. And we'll want to check and make sure that, you know, the outside and the inside terms together make that correct. Negative 4x and negative x ought to give us a negative 5x. And a 3x and a negative 10x ought to give us the negative 7x. So now we're factored. We cancel the x minus 2's. We will rewrite this, and we will make sure that every time we write limit as x approaches 2 until we start evaluating. So we got the limit as x approaches 2 of 2x minus 1 over 5x plus 3. Now we have a new equation in here. First thing we should do is take that 2 and plug it in. And now, since I'm evaluating the limit by plugging in the 2, I do not need to write the limit anymore. I'll just say this is 2 times 2 minus 1 over 5 times 2 plus 3, or 3/13. Any questions or issues with that?
No.